This is code 12 and not a fault in this case. Note that all codes are repeated 3 times. Then it flashes 3 times. A brief pause and 3 more times. This would mean service code number 33. The manual indicates this is a problem in the manifold absolute pressure, or MAP sensor circuit. Code chart number 33 then gives a step-by-step procedure to pinpoint and correct the problem. On this 1985 Ford LTD, an analog voltmeter connected to the battery positive and the diagnostic connector, along with a jumper lead, will activate the self-test once the key is turned on. Note how the meter first pulses once to indicate it is in the self-test mode, then 6 times, pauses, and then 3 times. The code is 63. Let's watch it again. Code 63 on Ford products is the throttle position sensor, or TPS circuit, and the manual guides you through the check and repair sequence. On this 1985 Dodge Aries, the self-test is activated by turning the ignition key on, off, and then counting the power loss light flashes. In this case, we see 2 flashes, a brief pause, and 2 flashes, followed by a long pause. Then we see 3 flashes, a brief pause, and 2 flashes. These are followed by a sequence of 5 flashes, a pause, and 5 more flashes. In this case, the first 2 codes, 22 and 32, are false, and the last, 55, means the end of the test.
This built-in code system, while not requiring expensive test equipment to read it, can get somewhat confusing, especially if you happen to blink your eyes when the light flashed or the needle pulsed or someone interrupted you in the counting process.
Cadillac gets around this by displaying the actual fault codes through the electronic climate control temperature display digits. In this case, pressing the proper buttons activates the procedure, and following an internal self-test will display code 88. Then the actual fault codes are displayed, after which 88 will appear again. There are many other tests possible, but time does not permit them to be demonstrated. These diagnostic systems are now providing an incredible amount of information, and each year more is added. For starting and during initial warm-up, the computer issues fixed signals to most output controls. This is known as open-loop operating mode. Once the oxygen sensor and the engine temperature sensor reach predetermined input values, the computer switches to closed-loop operation. At this point, timing and fuel metering controls become more variable to assure reduced emissions and good fuel economy.
At any time during normal operation, should some key input or output sensors, or in fact main sections of the computer, fail to operate properly, the system automatically switches back to open-loop mode. This is often referred to as secondary, fail-soft, backup, or limp-in mode, and allows the vehicle to operate, although poorly, to avoid complete shutdown.
Carburetors and some fuel injection systems use a mixture control solenoid, which delivers constant mixture in the open loop mode, but variable mixture when in the closed loop mode. Connecting a shop dwell meter to the solenoid will tell us very quickly what mode the system is in. With the key on and immediately after startup, note how the dwell is fixed at 31 degrees. This verifies open loop operation. When the ECM switches to closed loop, note how the dwell begins to vary from 36 degrees to 39 degrees.
Switchover time from open to closed loop depends mainly on engine and oxygen sensor temperatures, so it will vary. Once you have confirmed closed loop mode, we can now begin some other quick tests.
First of all, partially closing the choke to create a rich mixture should cause the computer to issue lean signals to the mixture solenoid. The dwell reading has moved from 35 degrees to 50 degrees, which verifies this has occurred. Now, remove a vacuum hose to create a lean condition. The dwell now decreases to between 20 and 27 degrees to prove the ECM has issued rich signals to compensate. We now know the mixture control system is at least responding. No response or dwell change would verify a system problem, and further diagnosis would be required. The O2 or oxygen sensor can be bypassed to see if it is the cause of the problem. First, separate the connector at the O2 sensor, then ground the lead from the computer. This will simulate a lean exhaust condition and cause the mixture solenoid to go rich or the dwell to read low. Note how the RPM also increases. Next, hold the same lead in one hand while touching the battery positive with the other. This will simulate a rich condition, and the dwell should increase and the RPM drop.
On fuel-injected engines, these procedures will cause noticeable engine RPM changes as well.
Now, let's use a timing light to confirm timing advance system operation. Providing the ECM is in closed loop, the timing should advance with speed and vacuum, just as in a mechanically controlled system. Read and note the total advance at approximately 2,500 RPM.